Okay, in this video, we're going to continue our discussion of induction, and we're actually going to continue to talk about what's called the triangular numbers. So let's define them more specifically this time. So capital T for triangle, sub n, because they're at the nth step, and we're going to add, all the numbers from 1 to n. And as we saw last time, you can make a triangle out of these by just putting 1 on top, 2 below that, 3 below that, and so on and so forth. So we get these triangular numbers. And we proved last time that the triangular numbers are equal to n times n plus 1 over 2. Okay, but this time we're going to do something else. So there's another proposition involving these guys. And so this is proposition 4.3 from the book. And so now, let's just say let Tn be, we'll write this part in words, the sum of the first n natural numbers, then for any n in the natural numbers, we find that t sub n plus t sub n plus 1 has another nice closed form expression, which is n plus 1 squared. That's a little pretty formula, so we generally like that kind of thing. And we're going to prove this using induction. Okay, so this time I won't do a proof sketch. Let's go right into the induction. And so we'll go right into the proof. And so here's the proof. So we just need to communicate to the reader, first of all, that we're going to use induction. So we'll say we proceed by induction. Okay, great. So what's the base case? Well, the first natural number to which this applies is n equals 1. So that's the case we got to check. This won't be that hard. That's like t sub 1 plus t sub 2, which we can just go back and figure this out. That's 1 plus 3. Of course, that's equal to 4. But the important part is to notice that that's equal to 2 squared, because that's what the proposition tells us needs to be the case. All right, so now let's go to the inductive case. Okay, so the inductive case, I get let n be natural number and assume that t sub n plus t sub n plus 1 equals n plus 1 squared. And okay, so then we aim to show that if I add t sub n plus 1 plus t sub n plus 1 plus 1, we get n plus 1 plus 1 squared, or in other words, n plus 2 squared, right? Okay, so that's what we want to show. Again, we're just communicating what we're trying to do here. We haven't done anything yet, but it's important to communicate to the reader what's going on, right? What we're about to do. Okay, so now let's take a step in that direction. So notice that t sub n plus 1 is equal to 1 plus 2 plus blah, 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 plus n plus n plus 1, and t sub n plus 2 is equal to 1 plus 2 plus da 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 plus n plus n plus 1 plus n plus 2. Right? So And hence, we can write t sub n plus 1 is equal to, well, I see a t sub n sitting inside there, right? So it's equal to t sub n plus n plus 1, right? And then let me give myself a little bit more room here. And then t sub n is similarly t sub n plus 1 plus n plus 2. So we get something useful here. So we can calculate. Right, again, this is the kind of structure you expect when you're using induction, that somehow the n plus 1 state should be related to the nth or something previous, and the n plus 2 state is related to something previous, the n plus 1 state. So we can calculate now that if I add t sub m plus 1 plus t sub m plus 2, we get, well, let's use these observations. So we get t sub n plus m plus 1, and we get t sub m plus 1 plus m plus 2. I'm putting more parentheses than we need just to emphasize where things are coming from. But now let's just kind of put this all together. So that's t sub n plus t sub m plus 1 plus 2n plus 3. Okay, so now we need to make this work. So we're going to use the inductive hypothesis now, because we see right here the thing that we're allowed to use the inductive hypothesis on. So now we say, by the inductive hypothesis, we find that this thing we're trying to work with is equal to, well, the inductive hypothesis said that what I highlighted in red here is equal to m plus 1 squared, and then we have to add to it 2n plus 3. Okay, now we have to factor this out, because we need to kind of push in these other terms and then refactor at the end. So first we got to expand. Sorry, we got to expand this out. So we get n squared plus 2n plus 1 plus 2n plus 3. So now we can combine terms, and then we're going to refactor. So we get n squared plus 4n plus 4. And if you refactor now, you get n plus 2 squared. Beautiful, because that's exactly what we wanted, right? So now we're just going to end by saying, hence, by induction, the proposition must hold, must hold for all n. Perfect. Great. So that's our second example of a proof by induction. It turns out, though, that you can actually do this by a direct proof. And since the goal of this class is to practice proofs and different proof methods, it's helpful to see something proved two different ways. So now I'm going to give you a second proof where we just do this directly. Okay. So proof, second proof, not using induction. So by proposition, now this, maybe you would say this is a little bit unfair, because proposition 4.2 does require induction. I don't know of a direct proof of that. There may be one, but we did use induction for that. But then we can now, so now we know that Tn plus Tn plus 1, well, we have formulas for each of those things, right? That's n times n plus 1 over 2 by proposition 4.2. And then this one is n plus 1 times n plus 2 all over 2. So now we just have to do a bunch of algebra here, but to figure out what's going on, right? So that's like m times n plus 1 plus n plus 1 times n plus 2 all over 2, right? One big fraction. And then here we get, if you multiply this out, you get n squared plus n squared plus 3n plus 2 all over 2. So we get 2n squared, 2n squared plus 4n plus 2 all over 2. Notice everything's divisible by 2 in the numerator, so that's like 2 times n squared plus 2n plus 1 all over 2. And we're going to cancel the 2, so we get n squared plus 2n plus 1. But now we can factor and we get n plus 1 squared as desired. Okay, so basically we can prove this just by applying the previous proposition that we proved by induction, and then carrying out the algebra until we get the desired right-hand side. So very nice. We saw this proved by induction, and we also now see it proved directly, and that's our second example. And moving forward, we will look for some more examples of, or we'll see some more examples of induction.